This is homework 3, part C. So just a little overview of what we're going to be doing. We're going to be deriving the Fensky equation and the Underwood equation, and then using CoLab, we're going to determine the minimum reflux, respectively, for light key and heavy keys for in the distillate and bottom product. So what I have already drawn up is like a little diagram of more of a simplified version of our distillation column, with our vapors moving up through the condenser and then liquid going down for the reboiler, and that sort of loop, I would say. And we're going to start with our equation. We're going to take our vapor composition of our light key equals the K value of our, in our reboiler, K value of our light key, and then multiplied by the X, which is our liquid composition of our light key in our reboiler. We'll do that same thing for our heavy key. So everything's in terms of heavy key to our reboiler. So now what we're going to do here is we're going to basically go ahead and make this into a fraction. So when we have our light key R over our heavy key R in terms of our reboiler, then we have our KLK and then KHK, and I'm going to keep these separate for a second just to explain further. And we have in terms of R. So for this little section right here, if we recall that relative volatility is equal to Kx over Ky. In this case, this is going to be X, this is going to be Y. So we can just sum this to our alpha value, but for the sake of this problem, it's going to be in terms of our heavy key. But we got our alpha value, and then we can get rid of those R's. And we're left with LKR and HKR. And this right here is our Fensky equation. And so now to start with the next thing, go back to white. What we're going to look at is our X of K, but we're going to be looking at the tray below. So we're going to do n-1 of our our heavy key, n-1, which equals square of our relative volatility, multiplied by the heat of vaporization of our light key over the heat of vaporization of our heavy key, and that's in terms of the reboiler. And we're also going to look at our distillate. So we're going to have, in terms of our light key and heavy key, we have our alpha to the n, and we're going to have our LK over our HK. Okay, so now what we're going to get is we take the log of our light key for the distillate and our heavy key for the distillate over our light key of the boiling over our heavy key or boiling. This comes out to n log of alpha. And what we're essentially looking for to finalize the derivation of our Fensky equation is we're trying to get this n isolated. So how we're going to do that is simply cancel out our log a, divide that, and what we end up with essentially is, log light key distillate over our heavy key distillate over our light key boiling over heavy key boiling, and this just equals n. So we successfully got an R Fensky equation. Now we're going to head over to our Underwood. So for this, what we want to look at is, let's draw a graph. So what we see on this is we have our operating line, and then we have our reaction curve. Okay, I don't do that. And essentially what we're looking for is the pinch point, which on this graph, if we look and suppose take a point right here, we can draw that to our reaction curve to about here, and then you make this triangle looking thing, and this allows you to, I guess not estimate, but your steps will be put in, and this can help you find the composition for this reaction. So if we recall our V equals L plus D, we can put it in respective of yn plus 1, and then L x n I respect to n plus our distillate x I in terms of our distillate. And to rearrange this, what we see is yin is equal to ki times xin. And if we rearrange that, we get xin equals yin over ki. And this helps us because now we can get rid of this portion right here. So what we find is, and we can get rid of the n plus 1 for now. So just conceptually, get L yi over ki plus our d xi d. There we go. So now what we're going to do here is we want to get our yi isolated. So we also have right here 2 of them. So yi minus L yi ki equals d xi d. So we get left with yi equals dxi d all over should be d minus L over ki. And we can go ahead and get rid of this ki by dividing both ends. So we get ki dxi d over e times ki minus L. And we're going to go ahead and divide the ki by KR. We get dxi d over v ki over kr minus L over kr. And thing to note, this relates to our relative volatility. So in this case, ki over kr will be alpha with respect to I. So what we get is alpha I dxi d over do is alpha I minus L over v kr. And this term right here is going to be sum to phi. So what we get is, it should go d, we're taking the sum of our alpha times xi d over our alpha I minus phi. So this right here, that's better, is our Underwood equation. So now we are on the coding section of this. So I've already went ahead and uploaded our library and the variables that we have to use, starting with our alpha, which is going to be representing our relative volatilities relative to the heavy key. So we have our 2.5, 2, 1, and 0.7 values already plugged in, and we have our flow or F set as 1 and Q set as 0.5, which is our 50 mole% liquid feed fraction. And since it does mention that since this is a 4-component feed, which is equimolar, we have our Z variable defined as an array where we have it set as 0.25, 0.25 throughout because we have a equimolar 4-component stream. Our our light key IDX is set as 1, heavy key IDX is set as 2, and then our recoveries, what we have here is for ROKD, it is 95% for the light key, and then for our heavy key, it's 0.96. So let's start with the next line of code, which we're going to set as W. So F times NP underscore R, or where is it? NP dot R underscore let's see. We're going to have is our Z component of our light key. Then we're going to have 1 minus, this is RL KD times our Z at our light key, and then we'll have 1 minus RL or RHKB times our Z at our HKIDX. Then we'll have 0 times our Z at HKIDX plus 1 with our colon. I hope that works. I knew it. Okay, so this might be np dot r underscore. Now what we're going to do is define our Underwood function in terms of phi. So we get return jnp dot sum, and it's basically what our Underwood equation was. So alpha minus z divided by alpha minus phi. This is to multiply all of that minus q. Yep, there we go. And then we want to put this as a vector. So we're going to have our jax.jit function, and we're going to use jnp dot Underwood underscore vectorize sorry, this is supposed to be jnp dot vectorize. We're going to have our Underwood as our parameter, and then signature equals that. That should work. Yes. And then fig equals make underscore subplots. There we go. Next, we're gonna go ahead and define our phi's, which is np dot linspace 0.9 times np dot min of alpha, and then we got 1.1 times np dot max of alpha. We got 1,000 points. So make sure that works. Yep. And then fig dot add underscore scatter. Our x is going to be our phi's, and Gemini did get a little bit correct, but it's just Underwood underscore vec of our phi's, and then we're going to update our y axes and make the range equal -3 to 3. Okay, there we go. So now, this is not the end, we still have a little bit to do. So we're going to take our phi underscore root, and we're just going to optimize this graph. So optimize dot root underscore scalar, again, our Underwood, and x naught equals 1.5 dot root. And when I define xd, so that's equal to wd divided by np dot sum of wd. And then we're going to take our minimum reflux ratio and we take our NP dot sum of our Underwood equation that we found earlier. So alpha times xd divided by alpha minus phi dot, or not dot, underscore root, and all of that minus 1. Yep, I believe that's, let's just try that, yep, and then we just want to print that. So along with finding our graph, we can see that the minimum reflux ratio is 1.65, and that is after deriving the Fence equation and our Underwood equation.